So the last section in Chapter 9 is about graphs of quadratics. And I suppose it's a good idea to spend a little bit of time in review here and just talking about really graphing transformations, because that's really what this is all about. So y equals x squared. That looks like this. Y equals x minus 2 squared is the same graph, except it's moved 2 to the right. There we go. Think about it. When x is 2, y is 0. When x is 2, y is 0. How about this? Y equals x squared plus 1. Okay, so that just takes the regular x squared graph and adds 1 to it. Alright, so now how about y is equal to 2x squared? So every value of y in the regular graph gets multiplied by 2. And the result is that it's a lot steeper. And by the same token, say y is equal to 1/3 x squared. Each value of y in the original graph gets multiplied by 1/3, which makes it smaller, and so my graph is a little bit fatter. And I guess the only other one to talk about is y equals minus x squared, and every value of y that was positive now becomes negative, and so my graph looks like that. So these are the graphing transformations that you need to be familiar with, and you have practice with them. And now let's move ahead and talk about the general quadratic. So in general, we want to graph a general quadratic which is given like that. And the features that we're going to keep in mind are the vertex and the x and y intercepts. So we want to try to make sure we know what those are, if possible. In general, the x-intercepts, the roots, may be the most challenging ones to find. Now, if you remember from what we were just doing on the previous page, the form that we want is this. Okay, now this is what's called graphing form. And when it's in graphing form, we know a couple of things. We know that the vertex is going to be h comma k. And a, well, if a is greater than 0, it opens up. If a is less than 0, it opens down. If the absolute value of a is greater than 1, it's going to be skinny. And if the absolute value of a is less than 1, it's going to be fat. And the other thing that we can get, and we actually get it by looking at the original equation right here, which is the right place to look for this, the y-intercept is what we get when we set x equal to 0, and that's simply going to be c. And so the one that is kind of, maybe we can figure it out, maybe we can't, are the x-intercepts. Now we know that we can always get the x-intercepts by using the quadratic formula. And you know, if we have to find the x-intercepts, that's what we can always rely on. However, there are times when we can graph this without knowing exactly the x-intercepts. Okay, so let's move along. So in order to graph this, we're going to look at this. And this is graphing form. And in order to put it in graphing form, we have to complete the square. So as I mentioned earlier, when we were using completing the square to solve equations, we also can use it to graph equations by putting it into graphing form. So let's practice with that. So let's look at this particular one. First of all, we can make the statement right off the bat that the y-intercept is equal to 5, right? And does this factor? Well, indeed it does. It factors as x minus 5, x minus 1. So the x-intercepts are 1 and 5. So if I start thinking about what the graph is going to look like, here's 1, 2, 3, 4, 5. Y-intercept is 5. 1, 2, 3, 4, 5. So that point is on the graph, that point is on the graph, that point is on the graph. And now what I'd like to do is complete the square to find the vertex. So this is good review. X squared minus 6x, I take half of minus 6, which is minus 3, and I square it, and I get 9. Okay, so then I still have a, what do I have? I still have a plus 5, and then I have to counter by adding that 9 by subtracting 9. So these two things balance each other out, but what I've done now is taken this and written that as a perfect square. So I can write this as x minus 3 squared minus 4. And from that, I can get the information that my vertex is 3 minus 4. Now notice the vertex is 1, 2, 2, 3, 4. The x value of the vertex is directly halfway between the roots, and it'll always be that way. There's beautiful symmetry in every parabola. In fact, such beautiful symmetry that we call this line the axis of symmetry. And so if a point is here and I flip it over the axis of symmetry, there'll be one here. So for example, this y-intercept is 0, 5, so I go 1, 2, 3, I go another 3, 1, 2, 3, and that means the coordinates of that point are 6, 5. So I can always get a point that is symmetric to the y-intercept. And that's the heart of graphing a parabola. So let's practice with one or two more. Before we move on, let me just ask you about a question like this. We know what the roots are, we see what the graph looks like. So suppose I ask you to think about where is x squared minus 6x plus 5 greater than or equal to 0. So this is my y value. And I want to know where are the y values greater than or equal to 0. Well, if you look on the graph, the y values are greater than or equal to 0 there, and greater than or equal to 0 there. So that happens when x is less than or equal to 1, or when x is greater than or equal to 5. And that's a kind of a inequality solution that we want to be able to solve, and it's very easy to do when we see the graph of the quadratic. Okay, now we'll move on. Okay, so let's take a look at this one. Again, we look at it immediately and we can say, okay, the y-intercept is minus 30. That's quick. How about the x-intercept? Do we have a chance of factoring this? So if we say minus 2x squared plus 16x minus 30 is equal to 0, and we multiply both sides by minus a half, we come down to x squared minus 8x plus 15 is equal to 0. And that has a chance of factoring, doesn't it? X minus 5 x minus 3. So the x-intercepts, or the roots, or the zeros, are x is equal to 3 and 5. So we know a lot about this graph already. Let's try to take care of that. So 1, 2, 3, 4, 5. So there's a root at 3, there's a root at 5, and the y-intercept is minus 30. So a sketch is enough. So now what I want to do is find out what the vertex is. Now, what we didn't say before, but that we can say in a case like this, because putting something like this into graphing form can be a little ugly. For the vertex, the x value is always going to be minus b over 2a. So in this case, the x value is going to be minus b, which is minus 16 over 2 times minus 2, minus 16 over minus 4, or 4. Now that should make sense, because if we look here, here is my axis of symmetry, and that line is x equals 4. So now we have to find the y value, and to find the y value we simply put x equals 4 in for y. And so what we get is y is equal to minus 2 times 4 squared plus 16 times 4 minus 30. So the y value of the vertex is going to equal 2. So the vertex then is 4, 2. And so here we are at 4. Let's go back to blue. 1, 2. So there's my vertex, and there's my graph. Okay, it opens down, and we should have known that it opens down because of this negative 2. And if I was doing it on a decent scale, you'd see that it's a little bit skinnier, because this number here, the absolute value of that number, is greater than 1. Okay, let's try one more. Alright, so now we're looking at what looks like a fairly simple quadratic function, x squared plus 2x plus 5. So, just noticing things right off the bat. The y-intercept is 5. How about the x-intercepts? Well, this isn't going to factor, so let's use the quadratic formula as a practice. So x is equal to minus b plus or minus the square root of b squared minus 4 times a times c all over 2a. So this is going to equal minus 2 plus or minus 4i over 2. So the x-intercepts simplified to be minus 1 plus or minus 2i. And these are complex numbers, so they do not show up on the x-axis. Now, if we go and try to put it into graphing form, we have y is equal to x squared plus 2x. We take half of the 2 and square it. So we add that to make a perfect square. Then we have a plus 5, and then we balance adding the 1 by subtracting 1. So we can write this now in the form x plus 1 squared plus 4. So the vertex is minus 1, 4. Okay, so let's squeeze in over here and put in what the graph looks like. So the y-intercept is 5. 1, 2, 3, 4, 5. There's the y-intercept. There are no x-intercepts because the only roots that we have are complex. So this graph is never going to touch, never going to hit the x-axis. The vertex is minus 1, 4. So right here. So it opens up like that. And now if we want, we could say, okay, the point symmetric to the y-intercept is going to be right here. And so there we go. And that's what the graph looks like. And because my roots are complex, they never ever show up on the x-axis. So that's a good introduction and a lot of practice with graphing quadratic functions. And believe it or not, that finishes chapter 9, which means you only have one chapter left to go. Good work so far. See you next time.